here's all the IMFs, okay? Whenever I say IMF, I feel like I'm saying International Monetary Fund. It's a totally different realm of discussion. Anyway, so let's go into some properties of liquids: surface tension, capillary action, viscosity, vapor pressure. This viscosity thing we'll talk about a lot for lab. So let's just talk about surface tension real quick. Surface tension is the tendency of liquids to minimize surface area. So as a result, liquids tend to form spherical droplets to minimize the surface area. The sphere is the lowest surface area to volume ratio that you can have. Okay, so surface tension is defined as the energy required to stretch or increase the surface of a liquid. Usually, the stronger the intermolecular forces in a substance, the more surface tension you have. Okay, so for example, if you spill water versus liquid mercury, water tends to spread further and farther and form more film, whereas mercury tends to form droplets more quickly. And why is that? Because well, water has greater surface tension, so it can spread more. Okay, and still, the molecules are attracting to each other via hydrogen bonding, so you get this more spread out film because of this greater surface tension. Mercury, lower surface tension, so it tends to break up into droplets more. Right. Liquid mercury, what's the main intermolecular force in mercury, liquid mercury? What is liquid mercury made out of? It's just made out of mercury atoms attracting to each other via, is it polar or not polar, liquid mercury? It's just non-polar, right? Mercury atoms by themselves are not polar. So what's the strongest force you can have? Dispersion, right? Dispersion is the strongest force you can have if it's completely non-polar. So those are weak forces, and as a result, the droplets spread apart more easily, right? You have more breakage of that surface area. Okay, so that's what's going on there. All right. If you heat up a liquid, okay, so here's the surface tension as a function of the temperature. If you heat up the liquid more, the surface tension goes down. Right. In other words, you heat up water, it's going to want to form droplets more than spread out as a film. So as you heat up a liquid more, you're breaking up the attractive forces, which makes it break up into droplets more. Okay, so increasing the temp will lower the surface tension. Okay, here's another one, capillary action. Okay, another example of surface tension is capillary action. We have cohesive versus adhesive forces. Okay, and these occur simultaneously. Cohesion refers to the attractions between molecules. Adhesion refers to the intermolecular attraction of molecules to another surface. So this is used by paleontologists to decipher rocks from fossils at digging sites. This is kind of interesting. So before I fell in love with chemistry, one of the things that I thought I wanted to do as a kid was I wanted to be a paleontologist and go to these digging sites and dig up fossils and put together dinosaurs, because I love dinosaurs. And so I think my favorite dinosaur was Ankylosaurus. It was a herbivore, and it was all plated in the back, and it had a club for a tail, and it could break the ankle of the T-Rex as it was coming along. And I was like, that's so cool, big bad T-Rex gets his ankle broken by a herbivore. So I was just thinking about these things. So I was like, oh, it'd be cool to be like going out in the field, digging in fossils, putting together these fossils for museums and things. And then I could be like Ross Geller from Friends, be the paleontologist, and have a complex about people eating my sandwiches. If you've seen the episode, anyway. Okay, so as I digress. But here's the thing, with capillary action, if you're at a digging site, I don't know about you, but if you're digging up a bone versus a rock, it's kind of hard to tell the difference. Well, I've never been to a digging site, but it just looks like it'd be hard. Like you got the brush there, you're trying to brush it off, is it a rock or is it a bone? I can't tell. So apparently what I've read is that paleontologists will sometimes lick the rock to see if they can feel the capillary action of the ancient capillaries in the bone of the fossil siphoning up water off the tongue as you're licking it. It feels like Velcro. You know, so apparently that's like a real quick and dirty way of deciphering. And I really do mean dirty. It's dirt. You know, who likes to eat dirt? I don't know, but apparently archaeologists like to eat dirt. So, so that's an application of capillary action. I mean, there's lots of others, but I thought that was interesting. As far as adhesive forces go, when you're licking a rock, for example, your tongue is wet, it's got water on it, and the water wants to adhere to the capillary surface. Okay, it's a small capillary tube, so they call it capillary action because the liquid wants to move up into the capillary. So bone tends to be polar. Okay, and so the water wants to attract and glom onto that polar capillary. The cohesion, you know, what that does is once one water molecule starts to glom onto the capillary, it pulls other water molecules with it because of the hydrogen bonding. And that's the cohesion part of it. So first water molecule from your tongue goes up the capillary, that's adhesion. And then the fact that it pulls other water molecules with it is cohesion. Okay, that's the difference. Okay, next up is viscosity. Okay, that's the resistance of liquids to flow. As temperature increases, viscosity will decrease. Okay, and again, the reason why is because if you're heating up a molecule, you're going to heat it up and you're going to break the attractions between the water molecules, and that results in a more watery kind of liquid. Okay. So that decreases the viscosity. If you look at hydrocarbons going from pentane to nonane, right, you're getting higher molar mass. The viscosity gets larger and larger as you get higher and higher molar mass because the dispersion forces are increasing with higher molar mass. All right, so why would you maybe not want to put anything heavier than nonane in your car engine, for example, in gasoline? If it's too heavy, if it's too viscous, your car engine's going to seize up, or it's going to, the moving parts are going to get stuck, right? Or the fuel injectors aren't going to be able to inject the fuel with the right amount of timing, right, with heavier hydrocarbons. So that's how viscosity can affect car engines, right? Or viscosity of engine oil to keep the parts lubricated, for example. Here's an example with viscosity in action. So motor oil, speaking of which, so there's an SAE rating of motor oil. For example, SAE 5, I think mine uses SAE 10, or something like that. Anyone know what rating your motor oil is in their car? Have you bothered to look at it? I wouldn't be surprised if no one's looked at it. It's one of those things that just get the oil changed and move on, right? But if you read the owner's manual of your car, it'll have an SAE rating recommended for the car. And usually around these parts, California, you're looking at SAE rating of 5 or 10. So, so the SAE rating refers to the viscosity of the oil. So, I'll get to that in a second. So the lower the rating, the lower the viscosity, the higher the rating, the higher the viscosity. Back in the 50s and before that, they had to change the oil based on season. So if it was a really hot day in the summer, you would actually want to have a more higher viscous oil, like a higher SAE rating, because the more viscous it is on a hot day, it stays lubricated, like it keeps some of that lubrication. If you have too low of a rating during the summer, the oil would just want to fall and it wouldn't want to stick on the parts of your engine that need to be lubricated. You know, it's like it's like trying to lubricate your car in water, which doesn't work too well. On a really cold day, you'd want a lower rating because if you have too high of a rating at cold temperatures, the oil would want to solidify in your car, and that would be good too. So they have this SAE 20W-50, for example, and that's a multi-grade motor oil. So the 20W means SAE rating of 20 at lower temp, but the 50 means SAE rating of 50 at higher temp. All right, so it's like they basically have mixed hydrocarbons in there to give you both at the same time. And so now we don't have to change our oil by season. We just put one oil in there, and that's it. So I'm not sure what the numbers mean. Maybe it's, I don't know, maybe it's some arbitrary scale that they use. Kind of like electronegativity numbers that are made up, but it's used as a scale. I'll have to ask my dean about that. He's an expert in this stuff. Okay. So here's, this has to do with our lab today, actually. So rank the following compounds in order of decreasing viscosity if they were a bulk fluid. Okay, so these are examples of what we call free fatty acids. So this is an example of a fatty acid. Now that we've done line structures, now you know that these up and down lines here mean that there's carbons. It's like carbon, 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 carbon. Okay. What do you think would have the highest viscosity? A, B, or C? Just take a guess. I hear people saying B, and you would be correct. Why would it be B? Has no double bonds, okay, but what does that have to do with viscosity? It's straight. Okay, so remember, are these compounds polar or are they non-polar? Remember, for big compounds, the majority rules. So are the majority of these compounds, are they carbon and hydrogen, or do they have a lot of OH groups and NH groups on there? It's mainly carbon and hydrogen, right? You know, there's a little bit of polarity at the tail, okay, but for the most part, we're dealing with non-polar compounds. The dominant force for these compounds is going to be dispersion. And dispersion refers to stackability. And this compound in the middle, we can stack more easily than the other two. All right. So the more stackable a compound is, the greater the dispersion force is, the more viscous that compound's going to be in bulk. Okay, what do you think will have the least viscosity? This one or that one? A would actually have the lowest viscosity. All right, it's got the most kinks in the chain of carbon. So I think I said this last time, chemistry can be kind of kinky sometimes. Okay, the more kinks you have in the chain, the weaker the dispersion force is, and the less viscous it is, the more runny it's going to be. It's going to want to flow more easily. So in lab, upstairs, we'll do a process called transesterification, where we convert a triglyceride into different free fatty acids. Okay, but they'll be methyl esters instead of free fatty acids. I'll explain that upstairs. But and based on whichever oil you're working with, you'll have more or less viscosity. Okay. So here you got one kink. The more double bonds you have in the chain, the more kinkiness you have. All right, and the lower the viscosity. Okay, you might notice something here too, just to point this out. Is this a trans or a cis fatty acid? You might remember, or not, in a slide back in chapter 10, I talked about pi bonding and how you can't rotate double bonds because the pi bond won't let you twist. Right? You have to break that pi bond in order to twist. Okay, this is a cis fat versus this part would be trans fat. Okay, one up, one down versus both up or both down. So cis and trans fat refers to, with double bond, are they both up or is one up, one down? Right, that's cis and trans. Fish oils tend to be more oily because they're mainly comprised of cis fats. Okay, and cis compounds, cis fats tend to be more oily. And then, so if you buy fish oil for a supplement, for example, that's supposed to be good for you. Right? So unsaturated cis fats are actually good for you. All right, trans fat or saturated fat, bad for you. All right, why are they bad for you? They stick together more, they tend to glom on, and they're harder to digest, and may lead to more plaque formation in your arteries. Okay, so that's the relevance here with viscosity. So I used to go to Pepe's once a week for lunch with my buddy, and we'd come back from lunch, all that trans fat all that stackability taking hold in our arteries. We sit there after lunch, oh, can you feel it? Yeah, I think I'm having a coronary. Come on, transfect, move it. Yeah.
Just a quick question, you said stackability equals greater dispersion, which equals greater viscosity, right?
Yes,
Okay.
yes, right. And then the opposite is true, right? Let's see, more kinks, less dispersion forces, lower viscosity, right? The opposite, right? Okay, so any questions about viscosity? Sounds like a dull topic, but if you think about the structure, anytime you look at molecules, you got to think structure, function. And we'll talk more about this upstairs with fats. I'll kind of do more on that. Okay. Yeah. So the order was higher viscosity, lowest viscosity. This is the middle one. So it goes 1, 2, and 3. In terms of the highest and lowest viscosity. All right. Last thing, properties of liquids, there's something called vapor pressure. Okay, so when you have a liquid, it's gonna, if it's in a closed container, it's gonna have an equilibrium condition where at some point the gas above the liquid reaches an equilibrium with the liquid itself, and so the rate of vaporization is equal to the rate of condensation backwards. And so, like if you close a water bottle, for example, and you leave it there long enough, you start to see condensation inside the bottle, right? And that's when you have reached the equilibrium condition where you've got the rate of vaporization of water equals the rate of condensation back into liquid water. All right, so the pressure of the liquid at atmospheric conditions at normal room temperature is called the vapor pressure of that liquid. Weaker attractive forces will result in lower vapor pressure, right? So if something has weaker attractive forces, it means it wants to vaporize more. Did I say lower vapor? It means greater vapor pressure. Okay. All right, so something like water will have a relatively low vapor pressure because it doesn't want to vaporize. It's got hydrogen bonding, it doesn't want to vaporize. If you have a compound that's nonpolar, it's going to want to vaporize a lot, and that'll increase the vapor pressure. All right, so weaker forces, higher vapor pressure. Stronger forces, lower vapor pressure. All right, they're inversely related. If you increase temperature, you're going to increase the molecules going into the gas phase, right? So it's going to increase the vapor pressure if you heat it to a liquid. So the rate of change depends on the strength of the forces as you increase temperature. There's something called a boiling point, normal boiling point. That's the temperature at which the vapor pressure of a liquid is equal to 1 atmosphere. The lower the external pressure, the lower the boiling point of the liquid. Okay, so for example, will it take you longer to cook a pot roast up in Denver, Colorado, or will it take you longer down here in LA, Orange County? Or Mount Everest? Anyone want to cook a pot roast at 29,000 feet above sea level? That'd be a new one, okay. So if you look at different mountain peaks or elevations, Mount Everest, 29,000 feet plus above sea level, atmospheric pressure, very low. Boiling point of water, even lower. Okay, usually it's at 100, right? Versus at sea level, Boston, Massachusetts. Boston, they love the World Series. Okay, the Chowds got us this time. That comes from clam chowder, that's why I call them Chowds. Boston, okay. At sea level, water boils at 100, right? Why does the vapor pressure decrease as you go higher in elevation? So here's the thing, if you have less gas in the atmosphere at higher elevation, that means the equilibrium of the water is going to want to go into the gas phase more to make up for that lack of gas in the atmosphere. Right, so you got some particles in the atmosphere already, but at higher elevation you got less water in the atmosphere, so the water is going to want to boil more easily to get up to accommodate that lack of pressure. that make sense? Right, so it's an equilibrium condition. By taking gas particles out of the air, you're making more particles in the liquid to want to go up into the gas phase to make up for that lack of initial particles. And so as a result, water boils at a much lower temperature at higher elevations. At Denver, Colorado, the Mile High Cities they call it, water boils 6 degrees less in temperature. So will it take you longer to cook a pot roast in Denver or in Boston? So I can't boil water past 94 in Denver. Lower temperature means it's going to take me longer to cook a pot roast in Denver, right? Because the temperature is lower, the boiling point of water is lower, right? Whereas I can cook things faster, I can cook my pasta faster in Boston, because now I can boil water at 100, right? Denver, I can only boil water up to 94. It takes me longer to cook at that temperature. Anybody going out of town for the holidays? Higher elevation? Anybody got any family in Denver? I used to have family in Albuquerque, which was about 5,500 feet above sea level. You noticed it, you know. It took a little longer. All right. So there's your everyday life. Anybody like to cook in here? Anybody like to cook the pot roast? Right? Stay down to sea level. It takes less time. Okay. So again, it's all about vapor pressure. The atmospheric pressure is lower the higher you go. Okay, that results in the boiling point to be lower of the liquid. Right. Okay. Which has the highest normal boiling point of these? So you got different curves. This is vapor pressure as a function of temperature. Notice how the vapor pressure increases as you heat up the liquid. That makes sense. You heat something up, it creates more vapor pressure above. So of these 6 compounds, what has the highest normal boiling point? You almost don't even need to look at this graph. You can just look at this. Water boils pretty high, right? So let's see. So at about 25 degrees Celsius, this is room temp. Right? The vapor pressure is such. Okay, but this titanium tetrachloride, all right, at 25, it's actually a little bit lower. All right, so if something has a lower vapor pressure, it's going to have a higher boiling point, right, to get it into the vapor. All right, so this guy is going to have the highest boiling point. It's actually non-polar, but it has a really high molar mass, making it tough to boil, or harder to boil. So Ti tetrachloride, titanium tetrachloride, has the highest normal boiling point. So all substances undergo phase changes as a function of temp. Right? You heat up liquid, it'll melt, and then it'll eventually boil. And then if you go in reverse, right, you can cool things down and vapor will condense in the liquid, which will then solidify into solid. That's just the general nature of things, right? During a phase change, you have something called a dynamic equilibrium. And that's when the rate of vaporization equals the rate of condensation, or at the melting point, you've got rate of melting equals rate of solidification, right? And they call these dynamic equilibrium. The key concept I want you to take away from this: during a phase change, the temperature remains constant as long as there's some portion of the sample that's still in that phase. So if I have ice water, I've got water, there's ice cubes in it. I walk away, I come back, there's still ice cubes in it. Did the temperature increase of the water? Did it or no? It didn't, right? As long as there's still ice in that water, it'll still be at 0 degrees Celsius. Only once all the ice is melted will the water actually begin to increase above 0 degrees Celsius. That makes sense? So during a phase change, the temperature stays constant. Okay, when the water is all liquid, then it starts to increase in temp. Okay, and then let's just say you want to cook some pasta, throw some pasta, or boil up some water. Let's just say you leave the pot to boil for a while. It starts to boil. You come back 5 minutes later, it's still boiling. Did the temperature of the water increase? It's still at 100 degrees Celsius because it's still boiling, right? There's still liquid there that's boiling. Now, if I come back and all the liquid water is boiled away, okay, then the gas could actually increase in temp. Okay, but as long as you're still in equilibrium condition there, the temperature is going to stay constant. So this is going to look familiar to you maybe from Chem 107. We have something called heating and cooling curves. So temperature as a function of heat added in joules. Let's just say down here you've got solid ice, and then you heat up that ice and it starts to melt. And during the melting process, the temperature is constant. The phases that are present during the melting process are solid and liquid together. They're in equilibrium, they're in a dynamic equilibrium. At this point here, the substance is all liquid, and the liquid heats up to the boiling point, and then it boils. While the liquid is boiling, it's liquid and gas together in equilibrium. And again, during this phase change of vaporization here, it's a constant temp, right? The temperature isn't changing. And then as you go from gas to even hotter gas, the temperature goes back on the rise again. So these are called heating and cooling curves. During the phase changes, you've got an enthalpy of fusion and vaporization. So during melting, you've got Q is equal to M, where that's the mass of the substance, times the heat of fusion. And then for the boiling part of the phase changes, you have M times delta H vaporization, right? So there's a heat of vaporization associated with boiling. Remember though, when the temperature is going up, you can use MCAT. So does this maybe ring a bell from Chem 107, maybe? So we had phase changes in that class too, and it's MCAT. MCAT for the rising parts, and M delta H for the phase change parts. So phase changes are here, temperature is constant. That's why there's no delta T in here. But for the temperature rising, now we have delta T.